Welcome back to this module on exploiting TLP to improve Unicore throughput. In this lesson I will give some examples of block multi-threaded processes. At the beginning, in the introduction lesson of this module, we showed this hypothetical example where every thread would compute for 20 cycles, then would incur level 1 cache miss, then again would compute for 20 cycles and so forth. And it will also, once every 200 instruction, incur one level 2 mesh. Right? If we now implement block multithreading on this hypothetical contrived timeline, thread 1 will compute for 20 cycles, then we will have the thread switch overhead, which will be some cycles, which cannot be neglected altogether. Then while the level 1 miss is handled of thread 1, the thread 2 computes, and when it incurs its level 1 cache miss, then thread 1 is again able to compute. So basically in this contrived example, the execution of one thread hides completely the level 1 cache miss of the other thread. But of course this is exactly synchronized. But when T1, thread 1, incurs a level 2 cache miss, which has a much longer penalty, a much larger penalty than a level 1 penalty, thread 2 will execute, but when thread 2 also executes a cache miss, the CPU will become idle because there is no other thread to execute anymore. So to improve the utilization of our core even further, we can use more threads, but this of course involves a cost, and we need to be able to find these more threads. The performance, the utilization, this figure here is taken from a book by Culler et al., Parallel Computer Architecture, a hardware-software approach, and it shows the utilization in percentage. The y-axis shows the processor utilization as a function of the number of threads. Apparently, if we have one thread, then only slightly less than 20% our processor is busy executing threads. When we double the number of threads, the utilization also almost doubles because we can hide some of the stall cycles. Basically, the performance, the utilization increases until we hit the performance limit, which in this example is around 80%, and at that time the performance is limited by the thread switching overhead. Other costs, other expenses and considerations are: we need more store replication, we need, if we have more threads, the thread selection becomes more complex, we need to scale up the size of the translation look side buffer, because now we need to be able to up to 5 threads execute at the same time. And furthermore, in this example was very contrived, was very fictive, because in reality the cache miss is highly variable. The latencies are also variable and not predictable, depending whether the next memory level, next cache level will hit or not, and the overlap is never perfect. Can we implement block multithreading in out-of-order cores? In an out-of-order core, because we issue several instructions every cycle, the cost of switching threads is much higher because the number of instructions in flight at a certain time is much higher, because the number of instructions that need to be flushed for the current thread is much larger. Furthermore, the newly scheduled thread will take longer to warm up all the reservation station. So it needs more instructions to fill the pipeline. So the cost of a block multithreading, the cost of switching in a block multithreaded out-of-order core is much higher, and therefore it makes sense that there is no example of block multithreading in out-of-order cores. Block multithreading has been implemented in several processors, for example in the IBM i-Series S-Star, which has been designed for commercial workloads. IBM called block multithreading hardware multithreading, HTM. The S-Star processor is a 4-way superscalar in-order processor. It's 2-way multi-threaded with a 5-stage pipeline, and every time there is an L1 or L2 cache miss, a thread switch occurs. Furthermore, there is a mechanism in place, a timeout mechanism, so that not one thread can live lock the other thread because it constantly uses all the resources. Intel Montecito is also an example of a block multi-threaded processor, and they estimated, I will not read this out loud, this slide, they estimated that duplicating the architectural state has a cost or increases the chip size area by only 2%. This concludes this lesson. Thanks for watching. In the next lesson we will look at another form of hardware multithreading called interleaved or fine-grained multithreading. Hope to see you back.